Hello everyone. In this video, I'll present our project, Failure Mode Decomposition of Multimodal Hallucination. Our project compares LaVA RLHF and LaVA One Vision. The goal is not only to say which model performs better overall, but to understand how each model fails. I'll walk through our experimental design, code implementation, model inference settings, result-saving pipeline, and final experimental findings. In this project, we trace the paper lineage, identify a frontier model, use public code and checkpoints, and design experiments that explore concrete limitations. Based on this requirement, our assigned paper is LaVA RLHF, and our frontier comparison model is LaVA One Vision 1.5. We also include SFT Plus as a same lineage baseline. We do not train a new model. Instead, we design 23 targeted prompts to detect concrete hallucination behaviors. In this video, I focused on why these prompts were designed, how each model is loaded and called, which generation parameters are fixed, how outputs are saved and merged, and why and what the final conclusion means. The key question is not simply which model is stronger. Instead, we ask, do RLHF alignment or scaling or stronger architecture solve the same types of multimodal hallucination? For natural scenes, we test whether the model treats scene pairs as visual evidence. For example, if it sees a desk, does it assume there must be a keyboard? For counting and relation prompts, we test whether the model preserves object boundaries and spatial layout. For extreme OOD inputs, we test whether the model invents semantic content from noise, solid color, or simply geometry. So our focus is failure modes, not just one aggregate scores. This slide summarizes our model setup. For the LaVA RHF stack, we use the SFT plus checkpoint, specifically the LaVA RHF 7B version 1.5 224 SFT model. For RHF, we load the RHF LoRa adapter on the top of the SFT plus model. The code uses low A bits equals true and device map equals auto. The prompt format is the classic LaVA format: user, image token, question, and acceptance. For One Vision, we use the LaVA One Vision 1.58b instruct checkpoint. It is loaded with Hugging Face Auto model for casual LM and auto processors. One Vision used the QuantVL track template and project vision info. The required transformers version is 4.53. We use BF16 or FF16 loading with a 4-bit NF4 fallback when GPU memory is limited. The shared generation setting is greedy decoding. Describe style prompts use Mac new tokens 128. Short answer prompts use 32. And A2 open-ended prompts are inspected qualitatively. In this project, we made a One Vision inference errors, and this is how we fix them. The root cause is that the One Vision checkpoint was exported for Transformers 4.53. With Transformer version 5, loading can sometimes be patched, but inference can produce invalid logics and garbage outputs. Therefore, our final decision is to pin Transformer to 4.53 in the LaVA OV environment and hard block inference when Transformer is version 5 or higher. The README documents several fixes. For missing cache or conflict APIs, we use compatibility streams, including sliding window cache, layer type validation, set submodule, and role-related patches. For missing pet token ID, we copy it from generation config. For GPU memory or metal-based problems, the code detects metal parameters and retrieves with 4-bit NF4. For Jupyter Arc crashes, we use notebook variables instead of command line arguments. For prompts and decode mismatch, we use the QuenVL templates and decode only the newly generated tokens. The main idea is that version painting matters. A model that loads successfully is not necessarily producing valid generations. We use two probes suite with 23 total questions. The first suite is natural scenes, with 16 probes across 6 images. These probes detect existence, counting, spatial relations, attribute recognition, and open-ended description. Typical traps include keyboard, banana, people counts, front or behind relation, and abstract art. The second suite is extreme OOD, with 7 prompts across 4 images. These images include pure noise, a solid blue image, a geometric circle, and a noisy real image. The benchmark takes semantic absence, elevation stability, and basic perception. Together, the two suites test both real image rounding and model behavior when visual evidence is minimal or corrupted. The implementation is organized under my work directory. There are 2 environment files. LaVA RLHF is used for the SFT Plus and RHF model. LaVA OV is used for one region. The text images folder stores both natural scenes images and OOD images. The code commands emphasize 4 things. Both benchmark save schema version 1.0 edition files. One region must use transformers 4.53 because 5S can produce invalid logic. A2 is qualitative and not counted in score OOD accuracy. And JSON preserves the full raw output even when console or CSV display is truncated.